Hi guys, Chapter 25, Electromagnetic Induction. Alright, little introduction, little history here. Alright, we previously learned that moving charged particles create a magnetic field of their own. Well, scientists wondered if the opposite could be true. If moving charges could create a magnetic field, right, could a magnetic field then generate a current, an electric current, cause charges to move? So two physicists, Michael Faraday and Joseph Henry, started working on this. Alright, initially it was a bust. They brought a magnet close to a loop wire. Nothing happened. No indication on the meter that anything was there. Alright? But what they noticed is when they brought the magnet close, they had a flicker. When they took the magnet away, they had a flicker. While the magnet was sitting there when they wanted it to work, nothing. What they found was that the magnetic field had to be changing. The strength of the magnetic field changed as it got closer or further away from the wire, right? Because distance, as we learned with Coulomb's law, has a direct effect on field strength, right? So the magnetic field has to be changing to cause an electric current and in order to maintain it. So as you can see from the picture here, you can move the magnet around the wire, or you can move the wire around the magnet. Either one of those is changing the magnetic field strength that wire feels. That's what causes your electric current. So, this is called electromagnetic induction because it is inducing a current. Now, we know from Ohm's law that if you have a current, you also have to have a voltage, right? So, we've got both going on there. And Ohm's law also talks about resistance, right? Current equals voltage over resistance. Well, there's resistance in the wires and the meter and anything else that's connected up to this circuit. So Ohm's law is still obeyed here. Now, how can we increase that voltage? Well, you can increase the number of loops as you see in the picture here, right? You can increase the speed with which the field changes, right? You'd go real super slow. You might not even see any voltage. But you go really fast, you're going to see a voltage increase. Applications. You use them every day and probably don't even know about them. Traffic light detectors for when it switches to green. Metal detectors, your credit cards, your debit cards, hybrid automobiles, hard drives on your computers. All of that uses electromagnetic induction. All of it was a great discovery. Now, Faraday got credit for discovering this. He published before Henry did. Henry had a lot more insights later on, got some credit. But Faraday had the law. Right? He said that the law was induced voltage is proportional to the number of loops, cross-sectional area of each loop, and the rate at which the magnetic field changes. Right? We already talked about this a little bit. More loops, more voltage. Bigger area, bigger voltage. Faster field changes, bigger voltage. Right? Well, how do you make that happen? Well, the bigger loops and the more loops, that's obvious. But by making the magnetic field change faster, you can do that in three ways. You can move the magnet, you can move the loop, or you can have the current going in a loop close by changing. Right? Because remember, what we talked about before, you have a current running through a wire, it generates its own magnetic field, right? Well, if you have that current changing, like maybe it's an alternating current, then that magnetic field's always alternating, right? Well, then this loop of wire over here feels that, and it will induce a current in there as well. So there's different ways to do it. You don't even need a magnet for all the ways. Alright. Faraday's law still has to obey Ohm's law and follow that. So the current produced depends on the resistance, how the current's wired up, series, parallel, all that. And of course how much voltage is there, which depends on the loops, how fast the magnetic field is changing, and so on and so forth. Alright. Generators, right? Now, last chapter we talked about an electric motor, right? And that is the picture here on the left. Okay? Now, an electric motor takes chemical energy out of the battery and that feeds into the loop, and then the loop turns in the magnetic field. A generator is the direct opposite of a motor. You have mechanical energy going in, right? So see the hand turning the crank to turn the loop, right? Still in the presence of a magnetic field, well, that will create an electrical energy output, right? Okay? Now, how does that work? Here's a little explanation. All right. So we know we're inducing a current, right? But why is it alternating? Right? You know, if you're moving that wire in the presence of a magnet, you're going to get a current. But why is it alternating? Why is it changing back and forth? Well, remember, a magnetic field runs from north to south between the poles on a magnet, right? So we've got this top portion of the wire facing the north pole, right? Then when it turns, now is facing the south pole, right? So as the loop turns, the force of deflection, the current that it creates, the bias of the voltage, all that flip-flops as the loop turns over. Okay, as you can see here, right? Now, a good way to remember this is a magnetic field, which is depicted by these dashed lines, has to be going through the loop, right? So as the loop turns, there's times, like this right here and right here, when the loop's parallel, that there's no dashed lines going through there, right? Well, that's when it drops off to zero current. But you don't see that. Your lights don't flicker in your house, right, when a generator kicks on, okay? Because the generator's turning fast enough that that momentary loss is not detected, all right? So you get alternating current, right? So current going this way, then flips to zero. Now it's going back up again, down, alternating, up, down, up, down, up, down, all right? That's the way it goes. Generators only create alternating current. All right. Well, Faraday and Henry's discovery sparked others to have ideas. So Nikola Tesla and George Westinghouse, right? Westinghouse light bulbs, right? If you ever look on light bulbs when you go to the store, Westinghouse still makes light bulbs. They showed that electricity could be generated in large quantities, right? This is around the height of industrial revolution. This is when all those big factories were being made, right? So you had all this steam coming out of the factory smokestacks. Well, they directed that steam into these huge turbines that were in the presence of a big old magnet. And then guess what? Got electrical output. And they actually lit up a whole city, or at least a city block around each factory. All right? Transformers. No, not this kind. A transformer is a device that uses this idea of electromagnetic induction as a way to transfer electric energy. All right? Well, it can not only transfer energy, but it can increase or decrease the voltage carried. All right? Before we get into that, what is a transformer? Right? It's simple. Two coils of wire, right? A primary coil and a secondary coil. The primary is connected to an AC output, right? You see a plug in here, maybe plugged into the wall, plugged straight into Duke Energy. It's plugged in somewhere. The power source. Alternating current power source. The secondary coil over here, the output coil, is connected to whatever device you want to power on. The lights, the house, the stereo, whatever. Alright? Here's what it looks like if you saw one in real life. Okay? Now these two coils are connected by this iron core here, the iron bar, right? What that does, as we've learned in the past, is just strengthens that magnetic field. All right? How does it actually work? How can we increase or decrease the voltage? Well, if you increase the voltage, that's called a step-up transformer. If you decrease the voltage, that's a step-down transformer. Well, remember, what did Faraday's law say? Voltage is directly proportional to the number of loops. So all you got to do, change the number of loops, you'll change the voltage you get out. All right, here we go. Step up. You got more loops in the output than you do in the input. Voltage increases. Step down. Got less voltage in the output. You got less loops over there. All right, so simple, but yet used so much, and they are about 99% efficient in carrying energy over. Here's how it works. we got the primary voltage, right? Input voltage coming in from power source, divided by the number of loops in the primary coil. All right, well, that's got to equal, remember this is complete energy transfer. This has got to equal the voltage coming out divided by the number of loops over here. So you make a proportion out of this, and that's your transformer equation. Now, transformers, we know, relate energy from one to another, right? But remember how fast energy transfers is power, all right? Well, power, since it's based on energy, has to be the same in both coils. It's got to be, because conservation of energy, right? So the power into the primary has got to equal the power into the secondary, right? Power in equals power out. Well, we learned when we were talking about circuitry a couple of chapters ago that power is equal to voltage times the current. So if we make substitutions, then we've got voltage times current in the primary. It's got to equal the voltage times the current in the secondary. And you can see in this table over here to the right how all that plays out, and you can even make another proportion. All right? And there's transformers. Okay? Now, power transmission. Right? We're talking about all this power, the rate of energy being transferred. How does transformers, generators, all that play into this? All right? Well, all electric energy sold today from all your utility companies is alternating current. Right? Because it's easier to be transformed. Transformers are used, generators are used, so much easy. All right? We transfer large currents in wires because that actually produces less heat going over the greater distances. Power is generated from the power plant as about 25,000 volts, and it's either stepped up or down to as much as 750,000 volts when it's going through these big, massive industrial-like power lines here. But then it's stepped all the way down to 120 or 240 when it gets to our homes. All right? So let's follow this train. We got the power station here, right? That's where the power is generated, the energy is generated. All right? Comes out at about 25,000 volts. Gets to this huge transformer here, and it's stepped up to 750,000 volts, carried on these massive lines here through the countryside. It gets to this substation right here where it's transformed again, but steps down, maybe back down to about 25,000 volts. It gets to a distribution substation here, and that's where it stepped down again to around 440 if we're going industrial, or 240 to 120 if we're going residential. And that's how it works. Alright, now, this electromagnetic induction is a two-way street, right? Because we learned that a changing electric current can produce a magnetic field. And we just saw how a changing magnetic field can produce an electric current. So, if you got one, you got the other, which then creates another, which then creates another, and guess what? We got this whole propagation going here, right? Maxwell, James Clerk Maxwell, brilliant theoretical physicist from Scotland, found this propagation, discovered it, and it broke through all kinds of barriers. Right? If we've got a changing electric current here, which, you know, any charge has an electric field. So if they're moving, well, the electric field's moving. A changing electric field creates a changing magnetic field, which creates another electric, another magnetic, so on and so forth. And we've got propagation. We've got a wave, an electromagnetic wave that can travel. Brilliant. Busted through all kinds of inventions with that. It created the telegraph, then the radio, then the TV, then cell phones, then satellites. Now any wireless device you can think of all uses electromagnetic waves. All right? Well, light is electromagnetic. Okay? All light is electromagnetic radiation. Now, if we are producing an electromagnetic wave that has the same frequency as visible light right here in this spectrum, then we can see it. But if it's producing low frequency, then we may be down here in radio TV land. If it's produced at high frequency, we may be up here in the X-rays and gamma rays. All of this is light. It just depends on how fast that wave is moving, the frequency of it. All right? But, bam, it's endless possibilities with electromagnetic induction. All right? So